Hey, good morning, everyone. So my name is Cruz. I am a PhD student in the Department of Forest Materials at North Carolina State University. So today I'm bringing the final results for our paper sludge to fuel project. This is a project funded by the Department of Energy, and this is a collaboration between NC State and the National Renewable Energy Laboratory. Basically, the main objective of this project was proving that we can obtain hydrocarbons in the jet fuel range from lignocellulosic biomass, basically paper sludge, that I will discuss later further. What is this raw material feedstock for our project? So we have seen a couple of times these type of graphics, and then we basically understand that the increase or the growth in population will be reflected in increase also in the energy demand. These then, in conjunction with the oil depletion, will further cause an increase in the demand of bio-based products, including also biofuels. So the aviation industry is a good example of how companies are now facing these big challenges from the commitment of the government for carbon neutrality by 2050. As we know, the major players are actually now communicating the results that they have been achieving towards these main goals. So let me explain what is paper sludge. So basically, in the pulp paper industry, not all the fibers, not all the lignocellulosic fibers can be retained as part of the paper being produced. So some fine fibers are actually rejected from the process, from the system, and they are collected. And the main way to dispose of this material is actually simply landfill. So you just pay for trucking and then landfilling this material. So it is estimated that in the United States only, more than 8 million of wet tons of this material are produced in the United States, of course, mostly in the areas where paper mills are located. And this material is basically composed by, the dry portion is composed by carbohydrates, ash, mainly calcium carbonate, and also silica, and a small portion of liquid. So this characteristic of this material is actually very relevant, because when we think on lignocellulosic biomass, if we think, for example, on wood or crops residues, these materials contain a high amount of lignin, right? So the pretreatment for that type of raw materials is actually more energy demand. But in this case, in the pulp and paper industry, one of the steps is actually basically removing lignin. So in this material, the carbohydrates or the fibers are more exposed. Cellulose fibers are more exposed. So it is easier to transform those materials into other type of products. And then if we analyze the carbohydrates present in this material, basically we found that the majority of this material is composed by glucan, also called cellulose, and then followed by cyan and mannan and some other minor materials. So here, basically, we are displaying the catalytic pathway that we defined for the base case. So basically, we have different transformation stages. The first step is actually accommodating the raw materials for further reactions. So here we have the first step, which is basically removing the ash. As we saw before, ash can go from 40% to up to 70%, depending on the type of mill. So this is the first step, removing this ash. So this ash is not interacting with further reactions down the process. And then we process those cellulosic fibers using an enzyme. We're using CPEC3 from Novozymes. And the idea of this second step right here is basically chopping down the size or the structure of this biopolymers in order to produce basically sugars, monometric sugars. So in this case, after this step, we are actually accounting for glucose, mainly glucose, and xylose in an aqueous solution, which is also very relevant for this process, because most of the times when we are processing biomass, one of the steps required as a pre-treatment step is drying, which is of course using a lot of energy. But in this case, so within our catalytic pathway, we are actually performing all the reactions in an aqueous medium. So that is important from this energy consumption point of view. All right, so then after we achieve our glucose and xylose, our sugars, we perform a dehydration reaction. Here we have a picture of the dehydration reactor we use. This is located at Emerald in Golden, Colorado. And basically the intention for this reaction is actually removing water, right? It's a dehydration step. So we are transforming glucose into a hydromethyl HMF and furfural. And so at this point, we are using aluminum chloride as an acid catalyst for this reaction. So it requires acid point so we can perform the reaction. And also in the literature, it has been proven that using organic solvent is actually helping to improve the yield of final products. So the most preferred material or solvent for this step is actually dioxane. We were able to validate that. So we achieved the highest yield to HMF and furfural when we were using this solvent. So the values, the numbers for this reaction for the yield to this material is actually 71% maximum, and the yield to furfural was 84%. Then after we, and this reaction is occurring at about 180 Celsius, so it's an intermediate temperature. Then we take our fuel materials, and since we are targeting to produce a C9 to C10 type of final hydrocarbon, we need to add carbons to the structure. So this is why we're using alkyl condensation in order to increase the size of the molecule, the number of carbons in the molecule. So this reaction is actually occurring at a high pH medium. We are using sodium hydroxide as a catalyst of the reaction, and we are using MEK in order to achieve the C10 type of material and C9 type of product here. Of course, alkyl condensation cannot only occur on this secondary carbon or this primary carbon, but it can also occur in both sides. So it is very important if you want to narrow down the species in the final product to use the right conditions so we don't have products with these big size because we are targeting against C9 to C10. So after we perform the alkyl condensation, then we need to saturate the double bonds carbon right there. So we use a low temperature hydrogenation. We're using a palladium carbon catalyst and of course hydrogen to saturate the double bonds. Then after this step, we recover the solvent. In this case, again for the base case, we're using dioxane. And we are using a continuous distillation system to recycle this material. And we will have then the products, the blue ones are the intended ones for our alkyl condensation. And then we basically open up the rings and remove oxygen with this hydrodeoxygenation reaction. This is a reaction occurring again with a solid catalyst in a higher temperature, 300 Celsius degrees. And then at the end, this is the type of products that we are producing. So basically C10 and C9 hydrocarbons. So we use semi-economic analysis because we needed to know, like, is this really economically feasible or not? So this is the way that information flows in our files. So basically we're using Async to estimate the rigorous mass and energy balance. And then we are integrating our experimental data with also existing technology and information from Enron reports regarding cost of chemicals and cost of equipment, and also economic parameters. And with all of that, we basically estimate the minimum fuel saving price, which is basically the minimum price that we can, the final product would have in order for not to lose money. And we're using an internal rate of over 10%. So the investor might be doing also some money. And we perform the sensitivity analysis. The reason for having the sensitivity analysis is that we were looking for a tool that was letting us know which particles are more relevant in terms of affecting or impacting this minimum fuel saving price. So we can dedicate our time in the lab in the right variables, not just spending a lot of time, tons of variables. You have more than 80 process variables analyzed. So this is the sensitivity analysis result for the base case that we discussed, again using dioxide. So what we can see here is that the main, after analyzing these 80 process variables, we can see that the more important or more relevant variable is actually the consistency of fibers before the enzymatic hydrolysis. That is basically the concentration of the solid material in aqueous solution for the upcoming reaction, which is again chopping down these polymers and converting that into sugars. And then the second, number 2 and number 3 are actually associated to the ratio, volumetric ratio between the organic solvent and the aqueous part or portion for the dehydration reaction. And the third one is actually the loss of solvent. So we have, for our analysis, we have fixed the loss of solvent as 1% of the total solvent getting into the distillation, which is a typical value. So 1 to 3% is a typical value. I'm sorry, again, this is the minimum fuel selling price. So GG basically stands for gasoline gallon equivalent. So basically we transform the energy containing this material into as if it was gasoline. So we can compare with that value that is more common for everyone instead of comparing this with the price of jet fuel, which is a different value. Of course, very high number. So when after we performed this initial sensitivity analysis, then we understood two things. So the first one is that we need to perform our enzymatic hydrolysis at a higher consistency. And second is that we could explore a different solvent for the dehydration reaction so we can minimize the price of this material. So what we have here is a paper liquid equilibrium graphic for this is dioxane and water. So again, this is the liquid line and then the vapor line. And then here we have the vapor liquid equilibrium plot for the acetone water system. So basically, two relevant things on this graphic. The first thing is that dioxane is actually exhibiting an isotropic node with water. That means that if we use a regular distillation system to recover this solvent, we might not be able to purify or to recover a pure stream of dioxane. So about 18% of water might be also leaving the top part of the distillation column with this material. But if we analyze the acetone system, we can actually determine that we would be able to purify acetone, basically distill acetone, recover acetone at a very high degree of purity. With that means that we will not have non-processed elements running across this loop in the process. And the second important and relevant, takeaway from this graphic is that the top product in the distillation column for our system using dioxane might reach the 89 Celsius degrees. But if we are using acetone, this value can be reduced down to 56 Celsius degrees, which is the boiling point of pure acetone. Of course, it is important to mention that it is just not about how much energy we are using to recover our solvent, but also what is the difference between the yield of products if we use one or other solvent. So again, I mentioned that using dioxane, we were able to achieve 71% yield to HMF and 84% to purpura. But when we use acetone, actually those values are reduced. So 3% each of them. So that means 68% yield to HMF and 81% yield to purpura. So in this study, we analyzed 8 scenarios. So the first one is the one that I mentioned about before. So using dioxane as the solvent for this dehydration reaction, again, so we can sort pretty quickly. So we have the ice removal, enzymatic hydrolysis, dehydration, added condensation, hydrogenation, distillation to recover the solvent for this reaction right there. And then we have the deoxygenation reaction. You can notice that between these scenarios using dioxane and acetone, there is a big difference, and it is the location of the distillation column. So for the initial base case, we were using the distillation column after the hydrogenation. But then if we consider that acetone is also a ketone, this ketone can also undergo a condensation with the fuel materials. And if that happens, then we will be reducing the number of carbons of our final product in 1 unit. So we needed to relocate the distillation column from this area right here before the anode condensation. So this is the main difference in terms of process layout. For our base case, we were considering a typical consistency for enzymatic hydrolysis of 20%. This is actually leading to a pretty close value because the yield for this reaction is pretty high, it's 99%. So this is leading to a concentration of sugars after the enzymatic hydrolysis of also 20%. And we fixed this dioxane to aqueous volume ratio at 1.75 times. So that means that we are using 1.75 times the volume of dioxane compared to the aqueous solution that we're having in our reactor. So again, this is the base case. So the base case is a counterpart actually, or better say the alternative case number 5 is a counterpart for this base case, but instead of using dioxane, we are using acid. So that's base case and alternative number 5. For alternative case number 2, we decided to reduce this volumetric ratio just because of the initial result with the sensitivity analysis. So we saw that the amount of solvent in this hydration reaction was very relevant to minimize the minimum fuel selling price. So we performed the analysis, reducing this volumetric ratio right here and right there. So we have alternative case number 2 and alternative case number 6. And then we decided to run some experiments, increasing the concentration of fibers for the enzymatic hydrolysis. This is quite risky because the current technology for enzymatic for enzymes, they don't allow to run the process at very high consistency because the enzyme doesn't have too much chance to get into the fibers if the fibers are too concentrated. But anyways, we performed some reactions and we were able to achieve 97% yield at this value of 30% consistency. So this is alternative case number 3, and then we fix the same value for the base case in terms of the volume ratio right there for this dehydration reaction. And then we have the last 2 cases. So basically, we decided to just keep the same consistency because of this limitation in the enzymatic step. But then we could also remove water and increase the concentration of sugars by simply installing an evaporator unit before the dehydration reaction. So here we have the results for our thermodynamic analysis or assessment. So basically, we can see here that the first 4 cases correspond to dioxane cases, and the last 4 correspond to acetone. So as I mentioned before, using acetone is actually reducing the yield to one of our intermediate materials. So just by using acetone, we are reducing the amount of final product produced per year. So actually, the reduction is around 1 million of gallons per year reduction. Moreover, these values right there in black correspond to the minimum fuel selling price of 1 gallon for each case. So we can see that if we move from base case to alternative case number 7, we can reduce in a 30% this minimum fuel selling price. This value, of course, as we can see, is still pretty high if we compare this value with a $2 or $2.5, which is a typical number for comparison, right? But again, after this process optimization work, we were able to reduce this number by 33%. So here we have all the contributors for this value right there. So if you ask yourselves, like, why do we have these negative values right there? So this actually corresponds to the credits for disposing the sludge. So companies are paying $60, so we can take that as a credit. And for the base case, you can also notice that there is a little bar, blue bar right there, and this corresponds to an extra amount of power produced in the mill. So the distillation column is so big that we have also a big power boiler, so we can produce enough steam to heat up the boiler. And then this huge amount of steam that we will require can also pass through a steam turbine generator, and the amount of power is actually high enough surplus. So we could sell that. So those are also credits for this extra power, but it doesn't happen for the rest. So basically, for the rest, we have actually to buy some power. Then the second bar in importance is actually these dark orange values right there. This corresponds to the average return of investment. So basically coming from the capex, from the investment. So the biggest expenditure in the capex actually corresponds to the power portion of the plant, because we need to produce a lot of power and a lot of heat for recovering the solvent. Again, I mentioned that we are actually recovering at 18% plus amount of, mass of water in that. And then if we want to preserve the volume ratio between the organic solvent and the aqueous for the system using dioxide, and since we are recirculating water, actually the amount of dioxide that needs to be, like moving around this cycle is huge. Then we have the next variable right there. This one corresponds to the loss of solvent, so how much solvent we are losing in our waste streams. And the yellow one corresponds to natural gas. So again, so we can see how by moving from this base case to the acetone cases, we can reduce the amount of energy required, and this is directly associated to the distillation. There is also a relevant, the gray bars actually correspond to NK, but NK, we need NK, right? Because we need to increase the size of NK, so we cannot really play with that variable. And the blue bars at the bottom part, actually, they correspond to the use of sodium hydroxide, which is the catalyst for the algal condensation reaction. So if we think on that on the acetone systems or cases, we are removing acetone before performing the algal condensation reaction. We are also increasing the concentration of proteins. So we need more sodium hydroxide to achieve a pH of around 13, which is the corresponding value for the algal condensation reaction. So that means that if we also use acetone, then another variable is actually, coming out from the list as the most relevant now. And this is basically what we were able to validate with our sensitivity analysis. So again, we move from having the consistency of fibers and some variables associated to the solvent now to sodium hydroxide, so catalyst for the algal condensation reaction. So now this is the target now. These are the results. We submitted this sample to Washington State University. They are experts on analyzing liquid fuels. And those are the critical properties that they were able to contrast with our numbers. So you can see that the surface tension, viscosity, heat of combustion, flash point, and freeze point. So all of them, almost all of them are in the range, or even better. For example, when we consider the heat of combustion, our material has higher energy content, for example. This is due to a narrower dispersion of material. So we don't have naphthalenes and others, but we have a reduced list of chemicals there. So these are the results that we were able to actually quantify there. So you can see those are C10 and C9 materials. And they also help us with the star alpha distillation curve. So this is a cup actually. So they had to remove a portion because there were still some heavy materials resulting from this double condensation during the algal condensation, so having a bigger structure. So they perform a partial distillation, and then around 44% of our material is actually in the jet A range, so around 158 to 280 Celsius degrees. So those are the takeaways. So we were able to prove that actually this material can be transformed into a liquid material that could be blended with jet fuel and replace a portion of that material. Interestingly, the solvent for the dehydration reaction, which is a common reaction for several other type of analysis and systems to produce other type of materials, is actually a driver for the minimum fuel selling price. So that's a key part. That's a key result from our study. And as I mentioned, additional research is required in order to find a catalyst for the algal condensation reaction that can be easily recovered. Since we're using sodium hydroxide, so it is very difficult to recycle, but let's say that we can find a solid catalyst that could be easily recycled, that could be help in order to keep reducing the minimum fuel selling price of the product. These are some impacts of our results. So actually, Ryan Davis at Emerald, he validated our results, and actually for the biochemical platform analysis project, he's now using acetone instead of dioxane, and he also is mentioning this relocation of the distillation for not having this condensation on acetone instead of NK. And Dr. Ashutosh Mittal is now in search for solid catalysts for this reaction. So again, before this catalyst was not a key variable to minimize the minimum fuel selling price, but after replacing the solvent for this dehydration reaction, now this is. So he has found some interesting results with strontium hydroxide, but he is still working on them. So this is the team that collaborated and contributed to the research, and then my advisor, Dr. Sunki Park. And then with that, thank you so much, and we'll take any questions.
Thank you.
So the product gets dumped into a refinery, takes the final cut for jet fuel, diesel.
Yes. So so the intention is that we can use a portion for other applications,
Right.
but we were targeting specifically sustainable aviation fuel. We actually
Higher value.
went beyond and we did the emissions analysis. I didn't include it. I mean, it is there just in case somebody has a question. But yeah, so this portion was just intended to analyze sustainable aviation fuel. But yeah, the rest of the rest of this portion can definitely be used as a regular.
But you said the product was processed to a refinery to do the final split into diesel and jet fuel.
Yes.
Clarify.
Sure.
Where your final product went.
Yeah, no, thank you for that. Yeah. So this portion is going for sustainable aviation fuel and the other portion is going
Very high quality crude oil for a refinery.
So any more questions?
Thank you for the presentation. So I'm a research scientist working for MIT24. So I have a quick question for you. You have shown lots of technical economic analysis. So did you also consider life cycle analysis to evaluate the emissions?
Yes.
And what is the potential?
Let me see if I can. Okay, so yes, we actually, this portion was also worked with Dr. Juan Yao from Yale University and Dr. Kainan from North Carolina State University. So we actually performed a cradle to gate analysis. We use OpenLCA and the parameters from Tracy. So basically, we did not include distribution and combustion. So you can see that the boundary is closed right there. But yeah, we did that, and then we analyzed 28 different scenarios. So for the previous scenarios, we were using natural gas as the main source of power for producing steam and heat. Steam or heat and power. But then we looked to other scenarios. So these 1, 2, 3, and 4 are actually the same modifications in the process. So that meaning, for example, reducing this volume ratio of this organic solvent to the aqueous that I mentioned before. So the 4 scenarios for each solvent, right? So here we have natural gas, dioxane, and this is F stands for using an NK from a fossil base, which is the most readily available now, right? So we have NK that we can purchase, but that one is coming from fossil fuel sources. Then we have these other scenarios right here with the W. The W stands for wood pellets, so another source of power for the boiler. And this D is dioxane, so those 2 cases are considered dioxane, but those 3 cases are considered actually acetone. So that is the distinction between the cases, right? And then we have again a difference here. So this is fossil fuel based NEK, but this is bio-based NEK. So that would be also a contribution. And then the last scenarios, the last 4 actually correspond to wood pellets, and then acetone, and then bio-based NEK, and also utilizing the ash leaving the process. So we would be taking this ash and sending it to the cement industry. So replacing a portion of the materials that they use there. So in order for us to call it sustainable aviation fuel, we need to reduce at least 60% of the emissions. So compared to the benchmark. So the benchmark is actually, so petroleum-based jet fuel is actually having 84.5 grams of CO2 equivalent. So that means that we need to be below 33 grams of CO2 equivalent. And only these case, so the values, the resulting values are actually these dots right there. So the only case that is actually accomplishing with that is if we use wood pellets, acetone, bio-based NK, and if we utilize the ash. Otherwise, all those other cases are avoiding us to call this sustainable aviation. So that's one thing. And the second thing is that we can also take some credits. Credits, of course, will reduce the minimum fuel selling price because we are taking just, like we can say to the government, like, oh, we are having this reduction, so we can take 1.25. If we reduce at least 50% of the emissions, CO2 emissions, we can take $1.25 per each gallon. And then we can increase in 1%, if we increase in 1% the reduction, we can take $0.01, so 1 cent. So anyway, so yes, we analyzed that. And again, so the only case that is allowing us to call it sustainable is this case right there. And the two cases that are allowing us to take credits are those two cases right there. And those values will reduce the minimum selling price. But again, the previous results that I showed was for the initial part of the techno-economic analysis only.
Okay, thank you.
Sure.
So our next speaker is Okuyami Fendi. Sorry, guys.